Luckily, I remember, otherwise no recording. So we have what is the latches in flip-flop is that we have past information, okay, normally comes from our current output that will be feedback to our circuit in order to determine our future outputs. Okay, so that is latches and flip-flop. Basically, we have memories. The combinational logic, that's what we learned from the previous chapter, is that the output depends only on the present input and doesn't have memories. Okay, so sequential logic is that we have memories. So sequential circuits, we have latches and flip-flop. Okay, and then we have further you've been introduced to synchronous and asynchronous. Okay, so synchronous is a synchronous sequential logic. We use a clock signal to regulate operation. So this is much simpler to design, and we have asynchronous sequential logics. Okay, so okay, can you guys try to let's say whether you remember our past lecture. Okay, um which type of this latches or flip-flop, which one of these is actually depending on the edge trigger? Is it latches or flip-flop? It depend on the clock edge. Is it latches or flip-flop? Can you answer at the Webex chat? Which types? Okay, flip-flop. Okay, the rest flip-flop. Okay, so which one depend on the clock state? How about clock state? Clock state means it depends on 0, 1. It doesn't it doesn't react to edges, clock edges. Is it latches or flip-flop? Okay, latches. Okay, so further define for this further define for the clock state is 0, 1. Okay, if it's 0, 1, we need to see whether it is what happened to our future output. Is it going to change? Is it going to not change? Or is it going to go through forbidden state? Okay, which can you guys tell me which of the previous, which of these circuit, which of these things, sequential logic that we learned in this chapter, which one have forbidden state? Which of the sequential logic having forbidden state? The state that shouldn't be having, but if we have that, it will create unconventional outputs, awkward outputs. Okay, which of these, the specific, which of the specific sequential logic that have forbidden state? Okay, at the minimum is SR-latch, SR-latch. So how are we going to solve SR-latch? Is that how is it? Okay, thank you. If we want to solve SR-latch, what is the circuits that what is the next sequential logic that able to solve the forbidden state in the SR-latch? I have asked this last time, but I ask again so that to see whether you remember or not. Okay, it's a D-latch. D-latch also known as what? The other name of D-latch. Okay, good. Okay, so means that you pretty much remember. Thank you, everyone. Although I know it's the same person that responding to me, it's okay. You responding to me, then you learn. The rest didn't respond, it's okay. Continue like watching movie. Okay, no problem. Okay, so we have been touched about this bistable circuits. Okay, the most simple one. So this one is actually we normally don't have changes. If we want to have changes, we have to implement the changes. Okay, otherwise it will be loop. Whether we're going to have 0 or 1 as our outputs. Okay, so then blah blah blah. With until we touch until D flip-flop in the previous lecture. Okay, so now today we're going to go through to this T flip-flop. Okay, T flip-flop, I hope that you have watched the lecture video that I asked you to watch. Who have watched it? The part 2. The part 2 of the lecture video. Can you give me thumbs up? Nur Aina, okay. Joey, okay. Nadira, okay. Ayu, Nur Shakira. Nur Akila, did you watch the second part of the video? Okay. Okay, if you watch, inshallah, it'll be better for your learning lah. Because like I told you, 2021 lecture video is complete, like 99, like 90%, something like that, complete. Then what I do in the current class is we top up because if I provide more video, it's become more longer and also no point for you. Okay, because I will not get the to add on twice the content. So it's better I concentrate on the exercise. Okay, because whatever that 2021 we have will not be covered in detail. Okay, because you already have that video. Now we try to focus on the exercise. Okay, in the end, exercise you will determine whether you understand the topic or the mistake made. Okay, so I will see the mistake and we learn from one another, from each other's mistake. Okay, so this is the T flip flop. Okay, by the name T flip flop means we have a toggle. So we have a toggle state. So if you see, this is the circuits for the T flip flop. Okay, this one is the way it look outside. Okay, then we see this Q and Q bar. Okay, again there is error, so this one is please correct your slide, the one that having the slide already. Can you correct your own slide, because this one is supposed to be bar. Okay, correct your own slide. Okay, so it's Q bar. So Q bar, then this T is your input, then this is actually a edge trigger. Okay, like flip flop is edge trigger, whether it is a rising edge or falling edge or positive edge trigger or negative edge trigger, something like that. Okay, so this one is positive and it's rising, so that's why we don't have bubble. Then this further define that that flip flop is a sequential circuit, so it will have the past information. So the past information is being fed back to here, and we are using XOR function. Okay, XOR function. For example, is the clock. If the clock is 0 and 1, there is no changes because the flip-flop doesn't depends on the clock state, but it depends on the trigger. Okay, then we go to the edge trigger, okay, which is a positive edge trigger, rising edge, and you see here is 0. Okay, when we have the t0 at this time, the t flip-flop will hold the previous values. Okay, it will hold the previous values. That's why you have the function hold. And when you have the next rising edge trigger, at that time, if the t is 1, it will toggle. What does it mean by toggle? It will inverse whatever previous output that you have. Let's say previous output you have 1, then the next Q plus will be 0. If the previous one is 0, then the next one will be 1. That's it. Okay. So where's the module? Because the slide, okay, you can refer to the module as well, right? Okay, but the slides doesn't have this information. Let's see, where is the page? Wait, where is your T free flow in the module? Okay, module page 144. Okay, can you share the photo 144? Ayu, can you share to the Telegram group page picture 144? Okay, module 144. Can you share to the group? Ayu? 144. Now. Are you in the class? Are you in the class? Can you share page 144? Because not all of your friends have the module. Okay, very slow. Never mind, I can do. Okay. Okay, so now I'll refer to no 144, the new 144. Is this old one? The one that's showing the wait, am I using the old book? Uh can you open the page where maybe I'm bringing a different book? I'm not sure. Share the pages that showing the T flip flop. The new one 142 142. Go to sorry because I have both books. I have both books, so it seems that I'm referring to the old book. It's okay. Can you share 142? The page that actually T flip flop. T flip flop. Can you share it to the class? The T flip flop pages. Maybe 142. Sorry. I'm using the I bring wrong book. Not wrong book. I bring the previous your senior book. Okay. Maybe. Okay. Senior book or whatever. Actually, for this year we have two version of module. The one that not really updated is the one that didn't have the complete answer. Didn't have I didn't have the word. Okay, the we have two version this year. The one that is initial one didn't have any label at the cover, and the one that newest one will have something like schematic answer inside. That one is the latest one. So I'm not having the latest one. I'm having the first version of this year edition. If you have uh, the the latest version of this year's edition, your page is 142. Your page for this different is 142. If you're having a bit older one, but still this year version, it is 144. Okay, never mind. Okay, wait. Okay, so you see these pages. Okay, so this is the T flip-flop. Basically, it's a XOR. Okay, we are connecting this to this XOR. Okay, so for example, if you see this is the H rising H. At this rising H, okay, the T currently is 0, so there is no change. So it will have no change to your Q. So it will continue. Okay, it will continue until here. And then let's say the T is changed in such a way that you have the 1 here, and you see the clock, the next Q output will be changed depending on the rising edge, not falling edge. So the next rising edge you have this T is equals to 1. Okay, T equals to 1 means it will toggle. It will toggle the previous output. So that's why this one is actually a toggle inverse of the previous one, which is 0 here. Then we go to the next rising edge. At this rising edge, the current T is 0. Okay, the current T is 0 means it will go to the hold status. So it will hold the previous value. That's why you continue to have 1 and so on. So this is the T flip-flop. Okay. The next one is the JK flip-flop. Okay, so JK flip-flop is instead of having one input as the I mean have one input as like a T, one external input. In JK flip-flop we have two here. Okay, then the similar as well we have inverted. Okay, I'm not sure why we keep having losing the bar button here, but it's okay as long as you understand. Okay, this one is actually just a typo, minor typo. You know it's a Q bar because we have bubble here. Okay. Where were we? Okay, so here we have 0, 1. again, because this is a flip-flop, it doesn't change when there is changes in clock state, but it's only change when there is changes in the edge. And the edge that we are referring here is actually the rising edge, not the falling edge. Okay, depends on what kind of edges that the things the flip-flop react to. If you have bubble here, means it will react to the negative edge trigger. So don't keep, for example, don't always limit your concept instead, because the lecture slide is always using positive edge trigger, positive edge trigger. Don't always stick it's always positive trigger all the time. Maybe in the exam you will get a question, instead of having positive edge trigger, it's a negative edge trigger. So instead of looking at this, you should be looking at here, which is the falling edge. Okay, so make sure you don't assume it's always be positive edge trigger. The question can twist a bit. Okay, then you see here, this is okay, let me see in the page again. I'm looking at the book. Where is the book for JK flip-flop? At which page? Okay, so there is JK flip-flop in the pages, but my pages is different than yours. Uh, can you share figure 10.34 inside the Telegram group? It's about the building JK flip-flop with a D flip-flop. Okay, so if you watch my lecture video, okay, if you watch my lecture video, previous 2021, I did explain that D flip-flop is the more common that we can use from this flip-flop to obtain a different kind of flip-flop. Okay, so D flip-flop can be converted to another type by implementing the characteristic equations. Okay, so I'm not sure if you guys share, if you share the pages. Wait, where's my Telegram? Hey, wait, where is it? Hey, uh, hmm, not sure what. Okay, close and open again. So if the question asks, maybe if the question asks what is the common flip-flop that you can be that can be used to obtain different kind of flip-flop. So the answer is D flip-flop. Okay, because from D flip-flop we can obtain another types of D flip-flop. I don't know why I cannot view the Telegram. I'm not sure. You see, where is it? I'm not sure. Okay, sorry for that. But it's okay. Nothing. I don't know what is happening. Okay, so JK flip-flop, if you see JK flip-flop is actually okay. Let me screenshot first. Okay, JK flip-flop is that if you want to see the characteristic table, okay, we have input JK, okay, and then we have because it's 2, we have 0 0 0 1 1 0 and 1 1. Okay, if we to obtain, okay, for example, you know that D flip-flop is like this. Okay, the most common one, the one that we can use to extend to another kinds of flip-flop. Okay, D is the like the basic like the basic flip-flop. Okay, you have, so this is your D. Okay, and then you have J and you have K. Then you have this one is actually the clock. This one is the clock, and then this one you having bar. Okay, you having bar in here. Okay, this one is of course clock. So I use different color. Okay, this one is clock. So this is actually your D flip-flop. Okay, this one is actually called your D flip-flop. But how we can obtain T flip-flop? Okay, how we can obtain the T flip-flop is that you just use the same D flip-flop. Okay, before we continue to JK. J and K. And then the same, you remove the inverter. Then from D flip-flop, you will get the T flip-flop. Okay, without inverter, you remove the inverter. But similarly, because this is a flip-flop, so you have a clock. Okay, depending whether it is a positive edge trigger or negative edge trigger. If it's negative edge trigger, you should have a bubble. Okay, the next one is to build a JK flip-flop from a D flip-flop. So now we want to have our D flip-flop. The same chip. Okay, the same chip of D flip-flop. How we're going to extend it to have a JK flip-flop. Okay, so the same D here. Okay, and then you have clock. Okay, you have a clock, and depending is a positive or negative edge trigger. Then you have your output Q. Then you have the inverted output Q bar. So if it's the inverted output, so means you have a bubble. Okay. Then to build a JK flip-flop from a D flip-flop is that now you have this J, then you have your K. Okay, J and K. Then in D you put a or logic. Okay, this one you can obtain the characteristic equation after you observe. You try to make the characteristic equation, characteristic table. Okay, then you will get to the equation later on. Okay, later on I will share. So this is JK. Then you have an N button here, an N logic. Okay, this one of course we only will have one input to our D, and then this one will be coming from this one and coming from this one. Okay, so this is J and this is K. So J is directly towards here, and this J is actually coming from the inversion. Okay, from the inverted output. Okay, and then the K we have an inversion. We have an inverted here, not gate. Okay, and then the next K, the next input is actually coming from our normal output, which is Q. Okay, so this one you can read. I mean, for better drawing, because I'm using this one using mouse, not that look pretty. So you can refer to the module and also online source. Okay, so the equation to have this JK flip flop, okay, is Q plus. Q plus means the next output, or present output. Okay, let's say we have this as we call it present output. For example, present output means the previous one we call it past output. If we call it future output, means the next future output means the current one is present output. So it's always it means the same thing. If past output, the next one will be present output. If the current is present output, the next will be future output. The same thing. It means that one is showing the later time, one is showing the previous time. So, but you should have this kind of wording. For example, past output, present output, or we have present output. The next one is future output. Okay. So this one is the characteristic equation. Okay. Okay. Now we go to the characteristic table first. Okay. This one. Where is the? Okay. Erase all in. Okay. Now we go to this characteristic table because we have JK as our inputs. So we have 0, 0, 0, 1, 1, 0, and 1 1. This is the possible combination for our JK flip-flop. Then the next step, okay, because it's a characteristic table, means you can learn from the what is the definition of the characteristic table, characteristic equation, excitation table from our module page. Okay, from our module page. If you didn't have the module, maybe you can ask your friend to help you whatsoever. Okay, there is you should know there is a characteristic equation, function table. Excitation table. Okay, there is different. For example, characteristic equation of a flip-flop specify the flip-flop next state as a function of its current state and inputs. Okay, so characteristic equation specify of a flip-flop specify the flip-flop next step as a function of its current state and input. So this is what we're having now is the characteristic table. So we have the next state Q plus. Then we have a current input, and also we have a current state. Okay. Now, let's say for the JK flip-flop, if it's both is 0 0, okay, 0 0, given that is a positive edge trigger, okay, means there is no change. Okay, given that is positive edge trigger at that time, so you can see this one no change. So Q plus will be Q. The next one, if we have 0 and 1, so it's like reset, it's like set and reset. So this one at the positive edge trigger, it will be reset to 0. Okay, when you reset, it's reset to 0 lah. And then 1 to 0 at the positive edge trigger, okay, it will set, means it will goes to the value of 1. Okay, and when you have XX here, sorry, when you have 1 1, it will toggle from the previous output. So if the previous output is 1, then the current output will be 0. If the present output is 1, then the future output will be 0, something like that. So it's toggle, okay, toggle depending on what output that you have previously. Okay, so this is a characteristic table. Then from this characteristic table, you're going to have characteristic equation. Okay, so we try to see the equation that will can be represented by this. Okay, so when you do the K-map, okay, whatsoever, then you will notice that this Q plus, okay, Q plus is actually equivalent to an XOR. Okay, an XOR for J Q bar. Okay, so if this is the XOR, means the next one is K Q bar, AKQ. Okay, so this is what we call as a characteristic equation. The next one is excitation table. Okay, you are being introduced to excitation table. Excitation table shows the minimum input. Okay, you see the wording here. Excitable show the minimum input necessary, means not all possible combinational of input, but the minimum input that necessary to generate a particular next state. So excitation table is different. You don't put everything. Okay, excitation table shows the minimum actually input that is necessary for us to generate the next state, particular next state. So mean you don't put all lah. Okay, so for the excitation table, you will have a present state. Okay, present state. So the wording here is present state, and then present state you put as a Q. Okay, or you can use if it's future, if it's past Q and its current will be Q plus. But this one is using present. So state means the next one is be future state or next state. Okay, next state. And then if this is Q, so this one is will be Q plus. Okay, means after. Then is the inputs. What is the input that going to contribute to this next state? So you have inputs of J and K. Okay. So you can see if you want to have this output, what is the minimum input necessary? So this is the JK. So let's say you see here, again, because it's QQ plus, so let's say you have 2 times 2 means 4 combinational potential combination. So 0, 0, 0, 1, 1, 0, and 1, 1. Let's say you want 0 to be 0 in the next step means there is no changes. Okay, there is no changes. So means that if there is no changes, if there is no changes means this 0 will become 0 again here. Okay, referring to the excitation table. Okay, in the page 145 at my module. I don't know what is the pages SEO module. Okay, 0. Let me write first all of them. Okay, if you want the future output have no change, okay, have no change to our Q plus. You can see here for the JK, this one is a bit, wait, this one is not SR. I don't know why it's used SR there. Wait. I think this one should be JK. Okay, wait. I think there is some, because this is not SR. SR is actually your SR latch. Okay. I don't know why is it SR. Why you put SR? It should be JK. Okay. Should be JK. Okay. Please make amend. Please make amend of your slides. Okay. So we have at this the same because it's flip flop for any clock state change, no changes. So that's why we have 0, 1 here. Okay. Means every of 0, 1 here, we don't care what is the input. We don't care what is the value for J, what is the value for K. We don't care. So that's why there is no change. Okay, then we start to have changes every of the rising edge. Okay, so let's say for 0, 0, we will have no change. 0, 0 at the rising edge, and then see for 0, 0, where is it? 0, 0. 0, 0 at the 0, 0, no, 0, 1, 0, 0. The rising edge. 1, 1, 1, 1, 1, 0. Okay, it doesn't have the, doesn't put the example, because we only look at the rising edge. Okay. Next, never mind, we see this first. Okay, at the next rising edge, let's say it is 0 and 1. Okay, 0 and 1. J is 1, K is 1. J is 0. Rising edge. Okay, this one. Okay, so this one is 0 and 1. Okay, 0 and 1. 0 and 1. So the next will be reset. Okay, the next will be reset. You see, 0, 1 will be reset. Okay, that's why you have reset here. And the next is J is 1 and the K is 0. Okay, J is 1 and the K is 0. J is 1, K is 0. Okay, J is 1, K is 0. So it will be having set. So that's why from 0, it's set to 1. Okay, and then at the next 1, 1, 1, 1, when it's a rising edge, so it's toggle. So from 0 is toggle to 1. Okay, and so on. So this is the characteristic equation of our JK flip-flop. So you can see it's like a XOR operation. Okay. I think when you do the exercise, you can know whether you know or not. Okay. Not sure if exercise. Last time you do only 10.1 and last time I asked you to do 10.1, 10.3 and 10.5. 10.1, 10.3 and 10.5. 10.5 is a JK flip-flop. So we'll be looking at the next tutorial, 10.5 for the JK flip-flop. Okay. I purposely also using the question that have the answer at the back, but you will see later on actually the answer is not always correct. Okay. So the next is we'll be discussing in the next tutorial. Okay, in the next tutorial, please do this before the next tutorial. 10.5 you have done it, but I will be checking it because we have yet to cover 10.5. 10.3 no, we will cover. I mean, you can ask me personally if you don't understand 10.3, but we have covered 10.1 last time. Okay, so then try to do exercise 10.5. Okay, 10.5 for the JK flip flop, and then 10.7 and 10.9. I will take in random which one to be discussed. Okay, means you have done this previously for the previous tutorial, and then you just need to do these two, 10.7 and 10.9. Okay, please try to do that. Please try to do that because if you don't do, then you will not know whether you understand or not. Okay, then we go to the next one is the flip-flop timing. Okay. This one is in the page of the last page of the chapter 10 latches and flip-flop. You have flip-flop timing. Okay. So you can see this is the flip-flop timing is like the operation times. So you have this is your flip-flop input. Okay, this is T setup time is the time a control input must be maintained before the clock transition. Okay, so this is the clock input. Then we have clock transition. So TSU is the time control must be maintained before the clock transition. So this is actually your TSU. Okay, the time control must be maintained before the clock transition. So this TSU, and TH is the whole time. Okay, the time control input must be maintained after clock transition. So this is your clock transition. Okay, so this is TSU, which is before it, and we have whole, which is after it. So this is your clock transition. Then TCO is the propagation delay from clock to output change. The time a flip-flop change after a clock edge is given. So propagation delay is that when actually in real life, when we have signal input signal, then it's not directly generated at that same timing at the output. There will be some delay. Logic, there will be some delay. So this is actually delay, okay, that been having the practical delay lah after from clock to output change, okay, from the clock transition until to output change. So you have a delay here, propagation delay. So you will not have wait. Okay, you can see this is actually the delay. Okay, is actually the delay. So if you didn't have the delay, you didn't have this TCO. Means whatever change here, okay, for example, every of the clock, it will change directly, but it is not possible to change directly because there is delay. So that is what meant by TCO, okay, propagation delay. And if you refer to the module, wait, I hope the question, the module did ask you to do some solution. Just now I asked you to do number 5, 7 and 9, right? 5, 7 and 9. Okay, 5, 7 and 9. So number 9, 10.9, a periodic signal is high for 200 nanosecond and low for 300 nanosecond. So what is the duty cycle? It's easy. Duty cycle is an active state over the total state lah, time. Okay, and then frequency of the signal is actually 1 over t, the complete period of one duration. Okay. So one duration is actually is 200 nanosecond plus 300 nanosecond for the question 10.9. So 1 over t is 1 over 300 nanosecond. Okay. So this one is quite direct. Okay. And then if you go to my e-learning, okay, if you go to my e-learning, or I'm watching Netflix, you show this one is Netflix. First skill. During lunchtime lah. I'm not watched during working time. Lunchtime just now. Okay. It's about vampire drama lah. Okay. So this is 3.83 and until 4.45. Okay. Which was because Assalamualaikum and this is new topic. This is new topic, which is the Assalamualaikum and good day. Okay, so today on the register. Wait. Is 29. Please make effort later on to watch this. Okay, 74. Okay. Synchronous. Custom. Okay. We start with why I keep covering the pages. 220. Okay. So this is about the counters. Okay, the next that you should be learning, okay, we have finished with latches and flip-flop. The next that you should be learning is register and counter, okay. Hopefully that you'll be able to, to do exercise, okay, 10.5, 10.7 and 10.9 for the next tutorial. And my quiz, where is my quiz? You see, the quiz will be covered from topic arithmetic logic circuit and also the latches and flip-flop for this weekend quiz. Okay. But I'm not sure when is the date. 18. Okay. And 18 until 19. Okay. Are you okay? I'm done recording. Are you I be on leave? Not on leave. Actually, I have to go